Welcome back. This is Fundamentals of Micro and Nanofabrication. I am Swayam Prabha from IIT Bangalore, and today we will have the final lecture on metallization, which is in the continuing series on additive processing, and we are discussing physical vapor deposition. So, let us get started. So, till now we have looked at various ways in which physical vapor deposition is done. Specifically, we looked at evaporation, sputtering, in much lesser detail, pulse laser deposition. Now, what we are now discussing is how the deposition of metal affects the properties of the devices. So, this sort of lecture would go into details such as electromigration, how do we deposit multiple layers of metals, and how the deposition, the properties of each deposition method affects the properties of the metal and then affects the properties of the device. So, the first thing we shall discuss is that in a modern device you often need multiple layers of metals. The best way to think about this is if you are connecting a city like Bangalore with roads, having all the roads in one plane often creates bottlenecks. You need to add traffic lights, there is a jam at the intersection, and one way to avoid that is to just have overbridges, and overbridges allow the vehicles to sort of go over each other and then do not have to stop. So, something very similar happens for very similar reasons happens in a device. So, what you are looking here is at a cross section of a real Intel chip. If I may, okay, this is missing the scale bar, but at the very bottom this is silicon substrate, and this is where all the devices exist. However, all the devices that exist in this layer and at this scale they are too small to actually be seen, then have to be connected with each other. So, if you look very closely, you will see right at the edge you can actually see two small metal connections, right. But that is not the only metal connections we have. Then there are another layer of metal connections, and then there is a second layer of metal connection, third, fourth, fifth, sixth, and you can keep adding. And as you keep going from bottom to top, you actually see that the metal layers tend to become larger, so bigger. And the reason for that is that the higher level metal are accumulating the current from the lower level metals, and as the current accumulates, in order to not have too much delay, they must have low resistance, and the way to get low resistance is to increase the geometry. So, top level metal layers are often very thick and very big in size, the lower ones tend to be thinner and smaller. Now, each of these metal layers must be insulated from each other, otherwise the signals will cross, and that insulator must be of the lowest dielectric possible. Otherwise, from the capacitance formula, you know, if there are two metal layers and you have an oxide in the middle, then there would be a capacitance, right. So, you do not want that capacitance because that causes delay. So, you want the epsilon to be as small as possible. Now, the best thing would be if all of this insulator was just air, but in practical devices that tends to be hard. There would be mechanical problems of having an overhanging metal. So, what we do that is we fill it with silicon dioxide, all right. So, this is the actual SEM. This is what an abstracted line diagram would look like. So, what you have is you have silicon, all right. This is where the device occurs. So, I am not showing a device. Then you have some layer, typically a silicide, which actually makes the contact with the metal. This allows lower contact resistance. We shall discuss what that means in the next few slides. Then you have this black thing which is touching the silicon titanium silicide. So, this black is also a metal. Typically, it tends to be a deep fill. It is called a via, VIA, and we will discuss what those vias are. And then this via connects you to the first layer of metal, which is M1. And then if you want to make a connection between the first layer of metal and the second layer of metal, you again need a via. And similarly, between a level 2 and 3, you again have a via, etc., etc. As you go up and more, the dimensions increases and the thickness between the metal layers also increases. Okay. Now, we have discussed enough about metal. One comment about the silicon dioxide. So, we have discussed several ways in which we deposit silicon dioxide. Now, the native oxide growth, which we discussed first, gives you very high quality silicon oxide, but it requires silicon. So, it should be obvious to you, because it requires silicon, these top layers of silicon oxide cannot be native oxides, right, because they do not have access to the silicon. Maybe the bottommost layer can be, but no more. So, it must be a deposited oxide. But there is one more additional consideration. You see, all of this silicon dioxide is being deposited on top of these metal layers. And if is one thing we have learnt in the diffusion lecture is that metals diffuse very fast. So once you have deposited a metal, you can never take the wafer to high temperatures, which means all these deposited silicon dioxides must also be deposited at lower temperatures, low enough so that the metal does not diffuse. So all of these silicon dioxide tend to be low temperature deposited oxides, and low temperature deposited oxides tends to have poorer properties, and that is something we have to deal with. And the last point is that this is what so we discussed the term back of the end processing, but we did not go into detail of what that means. This is back of the end processing. All these silicon dioxide depositions would be considered back end because they are being done with metal on it, which means you cannot do a lot of the RCA cleans that we have discussed. So you have to do a lot the more gentler cleans that allow metal to be used. You cannot use clean furnaces to these steps. You must dedicate separate equipment that are metal contaminated, and you must find processes that are low enough temperatures that these metals do not diffuse from this contacts through the vias, through the silicon dioxide into the silicon. So metal cannot move from here to here. All right. So that would be my discussion of metal layers. Moving on. Now let's discuss a little bit about the metal silicon interface in the first place. So ideally speaking, metal silicon interfaces are Schottky barriers. Metals are very good conductors, semiconductors are reasonable conductors, but the interface can actually be a worse conductor than both metal or semiconductor alone. And the reason for that is that at the interface you can actually have a built-in field which actively counters any flow of electrons. How bad that field is given by this value phi b. Larger the barrier, smaller the current. So if you are using the metal as a contact, you ideally want to have as low a barrier as possible, so you can push as high a current without any without a penalty in ohmic losses, right? Because ohmic losses are just losses, they would lead to heating, and they would also require you to put more voltage than needed. Now, for a lot of devices which like to make a diode, they shoot for larger barriers, but for contacts, and that is the application we are discussing today, you want this phi b to be as small as possible. Now this phi b depends upon the metal work function and the silicon work function. In general, the less difference between the two work functions, the smaller the barrier. Now one way what actually happens in practical devices is the barrier becomes very small, then for all practical currents that we need to use, apologize for that. So all the practical limits of current that we need to use, for those currents this expression can be idealized into a linear behavior, and in that case we say that the barrier is so small that the device is not functioning like a Schottky barrier but like a ohmic barrier. So that is what we seek. On the right is an example of what such a barrier would look like. So what you are looking at is current versus voltage. This current is scaled with area, so it's amps per centimeter square. And I am giving you example of a contact on n-type germanium, but similar things would be used on silicon or any other semiconductor. And you have a case for a metal semiconductor junction which has a large phi b, so that is this open circle, and small bi, which are filled circles and filled squares. So you can see that with a large barrier what you actually get is a diode characteristic. So you push current in the forward bias, but you do not push any current in the reverse bias. Now this is a problem, because supposing you want to push an AC signal which has both forward and negative voltages, positive and negative voltages, if you have a diode at the interface, then that would be rectified, and that is bad. You ideally want this ohmic sort of behavior where it's both the same amount of resistance on both the negative side as well as on the positive side, so you have a linear looking curve. So the linear looking curve can only be achieved for small barrier heights. Now one easy way to achieve this is to change the metal work function. So in this case, for example, it's between zirconium and aluminum, but so zirconium and aluminum themselves have slight amount of difference. So if you look at these open circles, the blue one, if I am not wrong, is aluminum, the red one is zirconium. So both of them are Schottky like, both of them do not allow current to pass through in the negative bias, but aluminum passes a little bit more current than zirconium. So this is just the difference in work functions. But you get a larger difference if you actually do something called passivation. It's a word that we don't have to get into detail, but some sort of interface some sort of interface engineering that allows you to actually lower the barrier despite these materials having very different work functions. A most common way of doing that is to actually dope the silicon at the interface. So, the simplest metal junction would be metal deposited on silicon, but that is not what is commonly done when the goal is to make a good contact. What is typically done is you take silicon and you grow a very highly doped layer of silicon. So, if this is n-type silicon, this highly doped layer must also be n-type silicon. So, n++ silicon and then the metal layer. And what this allows you to do is it allows you to tune the band gap, the work function of silicon. So, that is one. The second thing, it ensures that the barrier, any barrier between metal and semiconductor is so narrow that carriers can effectively tunnel through it. And that allows you to effectively have a small barrier, all right. So, this is a common trick to actually get ohmic contacts even when the work functions do not agree, work function between the silicon and the metal do not agree. So, these and a few other tricks are what people use to make good contacts. Here is an example of what you can actually achieve. So, this is some published data on n-type silicon and p-type silicon. A few things to note. First thing, we are plotting specific contact resistivity on the y-axis. Please look at the units. This is in ohms centimeter square. Think about why the units are like this, and the simple reason is in any device, the larger the area of the contact, the lesser the resistance, right? Because the resistance scales inversely with area. So, whenever you talk of contact resistance, you have to talk about a scaled number, and that scaled number is specific contact resistivity, which has units of ohms centimeter square, right? So, you want to calculate resistance from it, you have to divide it by area and you would get ohms. So, if you plot the specific contact resistance, the first thing we notice that is always a function of doping, right? For lower doped films, the specific contact resistance is high, and for higher doped film, the specific contact resistance is low. And this is exactly what we discussed in the previous slide. If you can grow a highly doped layer at this interface, your specific contact resistance would be low. The second thing we notice is the specific contact resistance changes with what is the barrier height, right? So, for any barrier height, high doping is better, but if you cannot do high doping, if for some reason you cannot create a high doped region, then you must play with your barrier heights, and the lower the barrier height, the lower the contact resistance. This specific case is for two contact metals, one is tungsten, one is platinum silicide. How do we make platinum silicide? We shall discuss a little later. Similar sort of effects are seen on p-type silicon, where once again specific contact resistance is a function of doping. In general, higher doping is always better, higher the doping, lower the specific contact resistance, but specific contact resistance also depends upon the barrier. Lower the barrier, lower the specific contact resistance. Now, what is a silicide? So, several metals tend to alloy with silicon. So, if you for example put platinum on top of silicon and heat it at some given temperature, then platinum and silicon would form an alloy, and that platinum silicon alloy is called silicide. Typically, it requires some high temperature. It really depends upon the metal, but the range is typically 400 to 900 degrees C. This can form even with noble metals, because this is not a chemical process, it is an alloying process. Just like copper and gold form an alloy, or copper and silver form an alloy, that is the different carats of silver, gold, right. Similarly, gold and silicon can form an alloy, or platinum and silicon can form an alloy. Whether a metal and silicon will form an alloy is actually given by the phase diagram. So, if you remember I think the second or the third lecture where we discussed phase diagrams in very small detail, those are the types of graphs you need to see to evaluate whether metal will form a silicide or not. Okay. And what is the stable percentage of, so how many percent of gold and how many percent of silicon, again is this solid solubility, and that again is given by the phase diagram. Now, the reason silicides are interesting is that several silicides are conducting, very conducting rather, right. So, for example, moly silicide, tantalum silicide, titanium silicide, tungsten silicide, they are all conducting silicides. So, formation of this alloy is very beneficial because it allows you to overcome some of the challenges you have with regarding to barrier height and other problems. So, if you are having an issue with your contact because the work function of the metal and silicon are not matching very well, a common trick is to just anneal it at high enough temperature that you form the silicide, and then what you have is a metal silicide silicon contact instead of a direct metal silicon contact, and that allows you to often reduce the contact resistance. Okay. So, this is another trick people often use to actually get ohmic contacts on silicon. If the silicide has a very different work function, then it can also be used to form Schottky contacts. So, those are the cases where you do not want to make a contact, but actually want to make a diode, and in those some cases silicide is a more reliable way to form a Schottky contact. Now, why is it more reliable? That requires a little bit of discussion in the practicalities of metal deposition. So, we have discussed a lot of tricks that we use to clean the silicon surface, right, and when we have discussed why cleaning the silicon surface is so important, especially before critical depositions. But a lot of those cleaning steps sort of only work for native silicon that does not have metal, because if it has metal, then a lot of those acid cleans that we can't do because of chemical incompatibility. But even with all of those, even with hydrogen passivation, even with hydrofluoric acid dips, there is always a little bit of oxygen that always is there on a silicon surface. Similarly, when you deposit metal, we have discussed a lot about how we maintain purity of physical vapor deposition by making the base pressure very low, by keeping very clean materials, by keeping the vein free path long, by keeping the arrival ratios high, etc. But all of those are still limited in their effectiveness. For any given deposition, there will always be some amount of impurity that is in the metal. So, any impurity, whether it is at the interface of the metal silicon, any impurity that is within the metal itself, would slightly change the barrier, and since the contact resistance exponentially depends upon the barrier height, very small changes in barrier cause huge changes in contact resistance. So, practically speaking, getting a consistent contact resistance from a metal silicon interface is often challenging in practical production. Silicides give a little more dependable system, because silicides are a thermodynamically stable material, like so the alloy would form to its solid solubility. Despite small amount of impurities in the metal or silicon or at the interface, the silicide would form, and the formed silicide is a bulk material, it is not an interface. So, controlling interface properties is very hard, controlling bulk property is a little easier, and because those bulk properties are more repeatable, the silicide contact tends to be more repeatable. So, yeah. So, here is an example of the various types of silicides that can actually form on silicon. So, let us start with aluminum, which is one of the easiest and the most often used. So, I am trying to give you the barrier potential for both N-type and P-type silicon, and these are not expected values, like these are not theoretical values, these are actual measured values. So, now ideally speaking, the barrier potential between N-type, if you sum the barrier potential between N-type and P-type silicon, ideally speaking you should get the band gap. Now, any time that rule is violated, it is because the barrier potentials are a little more complicated, there are interface effects, etc. So, the barrier potentials, theoretical barrier potentials and practical barrier potentials are often not exactly the same. Those of you who have done a device course may remember image charges and a few other non-idealities that creep in. We shall not discuss those non-idealities. We will simply say that theoretical and practical barriers are often different, but theoretically the sum of these two should be the band gap. Now, what that means, if a certain metal gives you a very low barrier with P-type, it should give you a high barrier with N-type. So, when you want to make a contact, you really need to decide whether you are making a contact to P-type silicon or N-type silicon. Now, there is one exception to this rule, and this exception is when you create this very highly doped layer at the interface. When you create very highly doped layer, you in some sense become insensitive to the barrier. So, if you are insensitive to the barrier, whether it is P-type or N-type does not really matter, as long as it is highly doped, any metal would give you an ohmic contact. But if you do not have that highly doped layer, then you have to make a decision of which metal to use, and that decision will be guided by whether you are making a contact to N-type material or to P-type material. So, let us take aluminum, right. So, aluminum is very often used. So, we realize that it actually gives you a higher barrier for N-type than P-type, which basically means it will give you a higher contact resistance on N-type than to P-type. This is the resistivity of the metal itself. So, the metal itself is very conductive. We all know aluminum is fairly conducting metal, but that is not the only consideration we have. Often the resistance or the resistance of the whole system is not decided by the resistivity of the metal, but the specific contact resistance. Aluminum and silicon start reacting with each other, or rather alloying with each other. Reaction is maybe a little bad word, at around 250 degrees C. So, it does not take too high a temperature. Remember, aluminum melts at around 630 degrees. So, 250 for aluminum is a relatively high temperature. And so, the other flip side is that aluminum silicon interfaces are only stable up to 250. If you are depositing aluminum on silicon, do not heat your wafer after the deposition to more than 250 C, or you will see a change at the interface. Right? If you can live with that change, good enough. If you can't live with that change, then it might be a little challenging. So, this also the reaction, the temperature at which the reaction between a silicon and a metal occurs also tells you what is the maximum temperature that interface will be stable up to. Another very common material that is used is tungsten. Now, you may remember tungsten was a refractive metal, a high temperature metal that we used as a boat or as a crucible in evaporation. So, it has a very high temperature. Interestingly, it gives you a barrier for both n-type and p silicon, but not very large barriers. 0.45 is a relatively small one for p-type silicon. Resistivity is much higher than aluminum. Tungsten is not that conductive, but if you are using tungsten only in vias, then the actual length of the contact is so small that the higher resistivity is something we can live with. The reaction between tungsten and silicon to form a silicide happens at 600-700 degrees C, partly because tungsten is a high melting point material, it sort of diffuses less, etc., etc. So, it means that you can actually make stable tungsten silicon junctions up to 600 C. Tungsten is often used for military hardened or space hardened devices for this reason. It's stable up to much higher temperature. Okay. Once you do form tungsten silicide, the tungsten silicide itself would have certain properties. So, the tungsten silicide, it turns out, has very similar properties to tungsten, and that is one of its great advantages, right. So, the barrier heights are essentially the same, resistivity is a little higher, but still on the same order of magnitude, and it is stable up to 1000 C, right. So, once you form the tungsten silicide, that tungsten silicide's interface would actually be stable up to 1000 degrees C, which is fairly high. The disadvantage here, of course, is this formation temperature. If you cannot tolerate these high temperatures because you have other metals that may start diffusing into the system, you cannot use tungsten. So, you start looking at other metals that form silicide at a slightly lower temperature, maybe not as low as aluminum, but maybe not as high as tungsten. So, common ones that people look at is nickel. So, nickel also has a lot of those same properties. It gives you a barrier potential with both, but relatively minor small values, not 0.8, 0.9, but 0.4, 0.5. Ideally, you start seeing ohmic characteristics for up to an amp of current at barriers of 0.3 or so. So, a barrier of 0.3 is, for all practical purposes, a pretty good barrier, a pretty low barrier. Nickel is fairly conductive, so that is another advantage. A reaction with silicon starts at much lower temperatures, 300, 600 degrees C. It really depends on what type of silicide you are forming. There are multiple silicides that nickel forms. So, which means that it is only stable up to 300 degrees C. Once you do form the silicide, it is much more resistive, but not too bad. Like as silicides go, this is pretty acceptable, but then it can be much more stable. So, you can actually keep nickel silicide once it forms stable up to 850 C. Okay. Titanium is another very commonly used metal. I will not go through the details of every one, but you see the general trends. Two materials that I will talk about are these titanium nitride and titanium carbide and titanium boride. So, titanium nitride we will discuss later is actually an extremely useful material. It is fairly conductive. So, you can look at its resistivity values are pretty low. It is stable up to 450, 500 degrees C. But more interesting, it is a remarkably dense material. Nitrides, carbides tend to be gems can be made, like titanium nitride is very, very hard. Titanium carbide is a very hard material. Borides are very hard materials. And because they are very hard and dense materials, they tend to not allow diffusion. So, titanium nitrides are often used as diffusion barriers. So, for example, if you have a metal and you are worried about that metal at a certain temperature will start diffusing out into the silicon, one way to prevent that is to encapsulate that metal by a barrier, and titanium nitride is an excellent barrier layer. Okay. So, titanium nitride we shall look into more details. Titanium carbide is sometimes used for similar reasons, and similarly for titanium borides. So, long story, so overall there are several details in how to make a good contact. You have to look at the barrier layer, you want the barrier to be low. If you cannot get the barrier low, you might want to form a silicide. If you cannot form a silicide, you might have to create a highly doped region in your silicon. The temperature at which your silicide forms, or the temperature at which the metal semiconductor interface is stable, is essentially the upper limit. Once you make that interface, the wafer cannot go to higher temperatures than that temperature. So, it's a number that you always have to keep in mind when you are creating your process flow. This is one of the reasons why metallization tends to be the last step in a typical fabrication process. So, you do all your high temperature sensitive steps first. So, you grow your gate oxides where you require very high amount of cleaning, you grow your silicon epitaxy where you require a very high amount of cleaning, and then from those very pure processes you then transition to moderately dirty processes such as RIE, etching, etc., and then finally you do physical vapor deposition of metal, silicides, nitrides, such that you do not create contamination. So, this is one of the things we discussed very early on when we discussed that how do we control contamination. And we control contamination by starting with a level 1 process which is pure and end at level 4 process which is contaminated with metal. So, yeah, so there is front of the line processing, there is back of the line processing. Finally, forming gas anneal. Now, we looked at forming gas anneal when we were discussing oxides, silicon oxide interfaces. And at that point, we discussed how forming gas anneal is essentially a mixture of hydrogen and nitrogen, but hydrogen is kept low enough such that the hydrogen-nitrogen mixture is a little more safe to use than hydrogen alone. The hydrogen in the forming gas is the active component, and hydrogen diffuses through materials very fast. So, it diffuses through the oxide and was used to passivate the defects at the silicon oxide interface. Forming gas anneal can also be used to improve the qualities of metal silicon interface, right. So, once again the forming gas is typically, the treatment is done typically at 400, 450 C, not higher. At any higher temperature, the hydrogen tends to desorb, not adsorb, and also at high temperatures, again, since the metal is involved, you take to high temperatures, the metal starts diffusing, starts forming silicide, things start changing. So, for back of the line processing, you want the temperatures to be low, and that is why you want to make sure that the temperature of the forming gas process is low. But of course, at these temperatures, if you have aluminum, then aluminum silicon starts forming silicide. But more interestingly, the hydrogen diffuses, right? The hydrogen diffuses, and it's a reducing agent. So, if you have any amount of oxide at the interface, which is preventing you from making a good contact between your metal and silicon, some of that oxygen might be removed because of the hydrogen. It might also passivate some of your defects that you are forming, because again silicon hydrogen bonds are extremely stable and extremely strong, and any defect at the interface can sometimes be compensated with the hydrogen in the forming gas. In fact, maybe I do not have a slide for that, but another very interesting aspect of hydrogen forming gas anneal is something called UL-NEAL. UL stands for aluminum, and the basic idea is that when you have aluminum in the system and you flow forming gas, then that forming gas reacts with the aluminum to form nascent hydrogen. So, not molecular hydrogen, which is H2, but nascent atomic hydrogen, and that nascent atomic hydrogen is actually much more potent at removing defects. So, if you have aluminum as a metal, your effectiveness of the forming gases are much better. One discussion on aluminum silicon interface, simply because so many people use aluminum silicon interfaces. So, if you look at the silicon solubility in aluminum, so till now when we looked at diffusion, we looked at the solubility of the metal or a dopant or an impurity into silicon, right. So, if you want to analyze how much aluminum diffuses into silicon, what you would look at is what is the solubility of aluminum in silicon. However, you must also remember diffusion is a two-part process, two-way street, right. Aluminum diffuses into silicon, but silicon might also diffuse into aluminum. After all, there is a gradient there too, right. So, we must also look at what is the solubility of silicon in aluminum, because that will tell you what is the rate at which the silicon will go into aluminum, not necessarily aluminum into silicon. So, this is plot of silicon solubility in aluminum, and you realize that aluminum is not very soluble in silicon, right. It is only around 0.001% at 600 C. So, aluminum does not dissolve in silicon a lot. If you look at the phase diagram, you will actually see nothing. However, silicon is extremely soluble in aluminum, up to 1%. right? That's a fairly large number, and that number increases at different temperatures. So, at 600 C, up to 1% of silicon is soluble in aluminum. Also, silicon diffuses remarkably fast in aluminum. So, any silicon that dissolves in aluminum because of solid solubility would also then move in the aluminum layer much fast. So, what that means is when you actually deposit aluminum on silicon and heat the system to say 500 C or 600 C, not only do you form a silicide, that is okay, but you sometimes form spikes. So, what are these spikes? These are spikes of silicon that was present in this film. So, maybe I should explain this figure a little better. So, this is silicon substrate, this is some oxide, you cut a hole in the oxide and you deposited some aluminum. So, this is aluminum. So, that aluminum is touching the silicon and you formed an interface, but then for some reason you took this to say 600 degrees C. If you do that, silicon at this interface would start diffusing into the aluminum. The solid solubility is high, the diffusion coefficients are high, and if silicon goes from here to here, then you would form a void, right? You would form a lack of silicon. And what will this lack of silicon be filled with? Well, there is nothing there, so aluminum will take its place. So, what actually that does is you create these spikes, you create these spikes in silicon, creates these, you essentially etch the silicon, and these etches can often short your devices. So, you had a very nice p-n junction, you deposited aluminum, you were hoping for a p-n junction and a diode, but because of these spikes you completely shorted your p plus. So, now your aluminum is in direct contact with n-type silicon, so you do not have a p-n junction, you just have a Schottky junction, and often that Schottky junction has a low enough barrier that you form a ohmic contact. So, you expected a diode, you would see an ohmic contact, and that is routine problem in two cases. One, if you take this system after deposition of metal to higher temperatures, and two, if your P plus regions are very thin. So, supposing you are doing rapid thermal annealing of very shallow implants, after that be very careful in using aluminum. If you directly do aluminum and do high temperatures, you might have a short. Even at low temperatures, you might have a short. The way to prevent that is to either use a passivation layer, say a titanium nitride at the interface, or grow a silicide, or do something to make sure the aluminum and silicon are not in intimate contact with each other. So, with that we come to the close of this section on metallization. In the next lecture we shall discuss another very interesting and known issue with metals, which is electromigration, and we will finally end with some discussion on the Damascene process and use of barrier layers. Thank you.